when we were first thinking about these sorts of things, we were thinking, or not even first, at some point along the line, we were thinking, people are talking about these things as in terms of fairness. So in Kleinberg, Mullainathan, and Raghavan, they present the disjoint two-group calibration condition as a fairness condition, pointing out that a score of B means the same thing if you're in group 1 that it means if you're in group 2, if the thing is calibrated on both groups. So when we think about it as a fairness condition, and we think about its significance sort of for each group, then comes the question of, well, which groups should we be considering? And this was really troubling to me for the following reason. Whose job is it, first of all, to list the groups? Who gets to say which groups are to be included in the list of quote-unquote protected groups, or the groups on which you're promising to be calibrated? Who gets to, who has to, whose responsibility is it, and who knows? And that may sound like a really strange question about, you might say, well, at least the members of the oppressed group or the subordinated group will know that they are subordinated, so that at least they could speak out. And that's not entirely clear. So first of all, it takes a lot of energy, a lot of fighting. And also, you have to be aware of the fact that something is wrong. And that's a lot less obvious than it seems. Wait, let me make sure, there it is. I'm looking for a slide. So that's a lot less obvious than it seems. So justification is a technical psychological term about an idea being used to provide legitimacy or support for another idea or for some form of behavior. And basically, what's being discussed in this very widely cited paper is that individuals generate beliefs about themselves in order to resolve a cognitive dissonance between what they think should be happening and what is actually happening. So if you have a subordinated group, this group can begin to believe that their poor treatment is appropriate, because otherwise the cognitive load dissonance is too much. So if you take that into account, then you can start saying, well, the people who are sort of in power may not be thinking about these groups either out of malice or out of just not thinking of it. They just didn't occur to them. And the people who are in these groups don't even know that they're supposed to be speaking up, or they may know it on some level, but there's some other level on which they don't know it. So the question then is there any way to kind of use technology to see outside, beyond our blinders, and come up with a really rich collection of groups that somehow is capturing all the ones that we want to capture? So with that question floating around, multi-calibration seems like a godsend. Oh my gosh, you can just specify some huge collection of sets, and now, as long as the groups that you're interested in can be identified in this set collection, then you're in great shape. So that's the appeal of being able to say things like, and let's not even worry about the other issue about whether the representation of humans that in the data is in fact sufficiently rich to capture all the things we want. Even if it is, there's still the question of listing the sets. So if you could say, as Guy mentioned yesterday, what if you could say that all polynomial time recognizable sets are here, or everything you can do with a poly-size circuit, or everything you can do with a circuit of size whatever, n squared or whatever. This would be fantastic. And in principle, you can, but then you have the agnostic learning problem. Then you have the auditing problem. So on the one hand, We're getting kind of everything we want in theory, and on the other hand, we don't know what is the right collection of sets to be using in practice. Okay, so complexity theory is great. It's a fantastic point of view, but complexity theory also tells us that these things could be hard. Now, some people would say, don't worry about it. There are heuristics. Machine learning is amazing. There are heuristics. We can do everything. And I don't know whether that's the right answer here or not. I simply don't know. And if anybody has a strong feeling about this, an informed feeling about this, I'm really, really interested in it. So if the class, yeah, okay, fine. And somehow or other, this is related to the accuracy problem. So we've been talking about multi-calibration. Guy has hinted at settings in which calibration does give us some kind of accuracy. But multi-calibration by itself doesn't do it. So for example, if you are thinking about your sets as demographic groups, and if the property that you're interested in is basically orthogonal to membership in the demographic groups, then multi-calibration with respect to the demographic group collections will not give you any kind of remote accuracy. So for example, again, if say the sets are completely random, for example, then if we just use as our predictor the average value, so we just take the empirical average, how many ones are there in our training sample, and we use that as the predicted value for each element in the universe, that's going to be approximately, this will be multi-calibrated. If you look at all of the people within each of these random sets, well, the average in the random set is going to be close to the average over the whole universe, and so this will be approximately a multi-calibrated. So, of course, that's a terrible predictor. It's ignoring pretty much, it ignores X completely. Once you've computed the empirical probability of a positive outcome, you just ignore the data. So that raises the question of, under what conditions is a multi-accurate predictor, multi-calibrated predictor actually accurate? So one natural situation, which Guy also mentioned, is when we think about the multi-calibration step as a post-processing of some artisanal, wonderful predictor that people have been working on for years and done a really good job on, and now we're fine-tuning it in the multi-calibration phase. So these artisanal things the machine learning people, the AI people have been wringing out all the inaccuracies to a great extent, and now you fine-tune it. Okay, so that would be one way of getting something even better, but you're already starting with something that's pretty accurate. So another way that a multi-calibrated predictor can give you accuracy seems to be that the collection of sets that you have is in some way smart. That is to say, some of these sets have kind of non-trivial correlation with the things that you're interested in. Like within your set collection, there are sets that are mostly people who are very likely to have a positive outcome. And there are sets that are people who are mostly very unlikely to have a positive outcome. So if those sorts of things, like imagine as a thought experiment, if the actual level sets of P star were in the set collection, then multi-calibration would immediately give you accuracy. Now, there is surely something in between. I don't understand that realm very well. I don't understand other conditions under which multi-calibration ensures accuracy. And as as Guy mentioned, part of the philosophy is, well, P star might be very, very complex, and we just have our measly collection of sets, and we're going to do the best we can. So that doesn't give you accuracy. It just says this is what we can do, this is what we can manage given the base collection that we have. But I'm very interested in this question of what are other conditions under which we could say that the multi-calibration condition really says something very non-trivial about accuracy. Okay. So with that understanding, I would sort of summarize this understanding as the sets, if you're not starting with an artisanal predictor, if you're starting at a half, the way Guy was discussing most of the time, the sets actually play two very different kinds of roles. One role is the fairness role of listing the demographic conditions, demographic subsets. And the other role is legitimate differentiation between the high probability of positive outcome, the medium tranche, the lower tranche, and so on and so forth. So it seems with this with this understanding, and I'm not saying this unconditionally, I'm qualifying this, but it seems that actually, the first comment is also true. And this is something that's worth thinking about. All of these algorithms that are calibrating and multi-accurate and so on and so forth, all of them are giving a description of the world as it is. They are not talking about what should be happening in an ideal world. They are not talking about how to do any kind of affirmative action. They're not talking about the fact that the world beats and depresses people and stereotypes, and when you stereotype, you lose information, and so on and so forth. So at best, what we're going to get from these things is a description of the world as it is, and then hopefully there's some way to adjust after that. It also seems that in this approach, both fairness and accuracy depend on the richness of the collection C of sets. And it's also the case that unless the sets have some very nice structure and have nice weak agnostic learning algorithms, the construction costs can incur a factor that's proportional to the size of the set collection. And so this suggests the following question. Using, again, the miracle of modern machine learning, is it possible that we could efficiently find a small but mighty collection of sets in the following sense? I'm going to call them scaffolding sets, and they're going to have the property that multi-calibration with respect to this collection of sets will yield a good approximation to P star. So that's the goal now. So again, as a thought experiment, suppose we could get our hands on the level sets of P star. Then if we could calibrate with, and that would not be a large collection. Let's say we're going to split up into multiples of 0.01. So that would give us about 100 sets. So if we could do that, then if we could calibrate with respect to this small collection, we would have accuracy. And if you have accuracy everywhere, then you get calibration everywhere. So it's kind of it's an attempted end run around the process of taking a given fixed collection of sets and having to page through them over and over again, coming up with a new collection of sets. So the scaffolding set problem is to do exactly that, to efficiently find a modest-sized collection S of sets such that multi-calibration with respect to S yields a good approximation to P star. And P star is calibrated on all large subsets, so our approximation to P star would be approximately calibrated on all large subsets. And what I want to argue is that sometimes we can. We don't expect to always be able to do it. But sometimes we can do it, and some interesting times we can do it. And when we do, these predictors are going to be calibrated on sort of all sets of positive density. So what's the philosophy that would be behind such an effort? The philosophy is, first, try to find a scaffolding set collection. So you're going to run an algorithm. You're going to run maybe some complicated algorithm, but nothing terribly expensive. And you're going to come up with a collection of sets. If you're incredibly lucky, this will be a scaffolding set collection. Multi-calibrate with respect to the set. If it's not a scaffolding set collection, it's small. It's not expensive to run multi-calibration with it. So if it's not a scaffolding set collection, running the multi-calibration algorithm, it's not going to hurt your accuracy. Guy showed us that. And, it may just be a no-op. But if it is good, it will take you to a very nice place. Now, you had your own collection of sets, and you might be deeply in love with your own collection of sets or have good reason to want to be going through them. So as a post-processing step, you can do whatever it is you wanted to do before. And if your algorithm is dealing with a very, very large collection of sets, and in some sense it is failing to solve the weak agnostic learning problem on this large collection, so be it. That would have happened anyway. But, and if it works, if it's, your algorithm is doing well with your collection, that's also fine. It's just post-processing. It's only going to make things better. If you get stuck, you can stop. So that's the philosophy. So we're going to do this and hope that it might be useful. And sometimes in some interesting cases, it will be very useful. So as I said, the hope was to use the magic of machine learning to find scaffolding sets. And the intuition that we're working from is the one that says that the intermediate layers in a neural net may provide high-quality representation of the input. There's a lot of work that tries to exploit this intuition in the literature, so we're adding to that tradition. And in what I'm going to be describing, I'm going to assume that you're given some kind of a, let me get my pointer. Okay. So you have your overall, here's the real world, and then there's a representation mapping that takes real world individuals and makes them input to the data set. That is some d-dimensional representation of individuals. And now we have some other mapping that takes the data as represented in d dimensions and maps it down to some much smaller number of dimensions, little r. And so when I talk about the representation mapping in the rest of this part of the course, I'm talking about this guy that starts with data and shrinks, does a low dimensional representation of that. So we're going to exploit the low dimensional representation mapping to build a small collection of sets. And it's going to actually give you a solution to the scaffolding set problem when this low dimensional mapping is good, and we will define what good means, but the definition is definitely going to have to take into account the data generation model that you're working with. So sort of stepping back for a moment, as Guy mentioned, if you have an artisanal predictor, and you start with that as your input, then you can, by multi-calibrating, you will only get better and you'll have good accuracy. And here we're saying that, well, if you start with some good representation mapping, whatever that is exactly going to mean, then we're going to be able to build a good scaffolding set collection. I'm flagging here that it might be much easier to get your hands on an H prime, or H prime itself may have much more simple structure than something close to P star does. So, yeah, okay. In our particular approach, the sets in our collection, in our scaffolding set collection, are going to be pairwise disjoint. And that makes multi-calibration with respect to this set collection extremely simple. But we don't need to rely on that, that's just a fact. So then we'll go through an accuracy analysis, which will discuss accuracy of the resulting predictor that we get as a function of whatever the goodness is of H hat. So if H hat is really bad and has terrible goodness, we're going to get nothing. If H hat is really good, as we're going to define it, then we're going to get something very useful. And then finally, we'll talk about some methods for learning a good H hat. I won't have time to talk about this, but there are some specific examples where multi-calibration with respect to the set collection that we get is more expressive than the underlying neural net class that we use to represent, to give us elements of S, which is again completely consistent with what has been going on until now in multi-calibration. Okay, you don't need to memorize these, but I'm just pointing out we're going to have some number of training points. We have a distribution from which the training data are chosen. We have a low dimension for our low dimensional representation R. Low dimension R for our low dimensional representation. H hat is our low dimensional representation mapping. And we're going to assume that H hat is mapping us into some bounded range. For some constant C, numbers are tuples with values between minus C and C. And we're going to get some number of what will be obviously quantiles that we're going to be using. And that number is B. That's the number we're going to use in each dimension. And the total number of sets will be B to the R, because we're in R-dimensional space. And so our set collection is going to have size B to the R, which is why we need R to be small. Okay, so the set construction is pretty easy. For the very beginning, let's just imagine that we'll do sample splitting, and we're going to use half the data points to do some set construction, and then the other half to do some calibration on that set construction. So we're going to use the quantiles of H hat to subdivide the range into not necessarily evenly sized cells, such that each cell holds about 1 over k of the training data points. So for example, we might partition the quantiles on the first coordinate and then recurse on the remaining coordinates. So we start up here and we end up with something that looks like this. And then there's a lemma, the adaptation of a lemma by Kumar Liang and Ma. And it says that suppose we started with n IID samples from our distribution, and we partition according to the method that I just described, such that each cell holds about n over k samples. Then truly, with high probability over your samples, truly these cells capture each about 1 over k of the mass of the underlying distribution. So that's great. So once we do this, we know that if we have done this sample splitting, we'll have plenty of samples to do calibration for these individual cells. So we're going to partition the range this way. The cells will be our pairwise disjoint sets. And we're going to calibrate each cell using the second half of the data. So we're going to estimate the probability of a positive outcome just by using the empirical means for the data points that map into each of these individual cells. Okay? Any question on how we're doing this? Okay. So, as I said, because of the lemma, with high probability, we'll have plenty of samples for each of the estimates that we need to do. And so, again, with high probability, our estimates will all be pretty accurate. And our simple predictor that we're going to construct is just on input X, figure out which of the cells we got mapped to, and then assign the empirical mean for that cell. So the predictor is very simple. And the theorem says that this particular predictor with this particular calibration method is this kind of multi-calibrated with respect to S with high probability. So notice that as n gets large, and we've made, B is some fixed constant. We made R pretty small, so K equals B to the R isn't too huge. So eventually the calibration error will be small. Okay. And, right, that's our simple predictor. So now I want to analyze this predictor. So the predictor that we get is going to work well when reality can be expressed as something close to the following. There is some wonderful H star, some ideal H star that maps the individuals as represented in the data to the lower dimensional space. And then this is followed up by some very low Lipschitz suffix, a boring suffix. So it's an interesting dimension reducer followed by a relatively boring suffix. When reality looks something like this, we're going to do well. So, so we need a couple definitions, or I need really one definition so I can tell you what goodness means, because that's a key point for us. So I want to look at a collection of functions. These are the functions of the form W that maps R dimensions. These are the suffixes that map R dimensions down to one dimension, and they're Holder smooth. And then for P star, for our actual truth, I want the set H of P star beta L to be the set of H's that can kind of get things nicely down to something in this set. So it's a set of all H such that there is a W in this set, this smooth Lipschitz-like W, so that P star is equal to, or equal to for now, W composed with H of X. Yeah?
So I just want to go back to a point you made a few slides ago when you said that H can be significantly simpler than P star. So the gap between the complexity of P star and the complexity of H is exactly this W here, is that right?
So, I think so.
And the point is that W could be quite complex. You're not...
No, W could be complex, but it has to be Lipschitz. Mm-hmm. So there are limits to what it can do. Mm-hmm. Mm-hmm. Right. Okay. So my intuition is that the really interesting stuff is happening in H, but then there is something important that happens in the suffix. Yes. Maybe I need to recalibrate my intuition. Okay, so now I can define goodness for you. H hat is epsilon H is EH good if There is some H, so that we could express reality as W composed with H of X. So there is some H, so that in expectation over our distribution, here's where our distribution is coming in, H hat of X minus H of X squared in norm isn't too big. So it doesn't, yeah. Okay. So when we talk about Lipschitz conditions, we're talking about for a fixed function H, what happens when we shift X a little bit. Here I have a fixed X, and I'm going between H and H hat. Now, as I said before, if H hat is bad, there's nothing we can promise other than we won't make anything worse. But sometimes you can get your hands on an H hat that's good, and we'll briefly discuss some conditions for that at the end. What am I saying here? Did I already say it? Right, P star can be expressed as a low-dimensional representation, followed by a boring suffix, and Guy points out the suffix may not be so boring. And then H hat is EH close in expectation to an ideal low-dimensional mapping. It is not the case that there's only one way of expressing P star as a combination of an H and a W. There may be multiple ways of doing that. Okay. So we're not going to be able to do anything, as we said, if H hat is bad. So let's assume that H hat is EH good for some EH greater than 0. And let's see what we're going to get. And then we need a technical condition that has to do with the density of the underlying distribution on the cells. And all I want to say about this is that there's constant density on the cells. So it's all kind of just nice and smushed in there. Okay. So let's assume that H hat is EH good and this technical condition. And let's assume that we have enough samples. And now let P tilde be any predictor that's alpha n multi-calibrated with respect to S. It could be the simple predictor that I described earlier. It could be the predictor that we obtain using Guy's algorithm. It could be any other multi-calibration algorithm. I don't care. Okay. Then this is what we're promising. This is the accuracy condition that we're promising. That, why do I have a D here in the distribution? Because D is also involved in the definition of the predictor. Like, we built those cells. So it's to remind you that we need it for that too. Okay? So the promise is that the expected squared error is bounded by this. L is our Lipschitz constant. B is this thing that's under our control. So basically this gets small. So the way I'm going to argue this, I'm not going to give you all of the details of the proof, but I'm going to give you a couple of the key steps. And over again, we're going to use this very, very useful fact. And so when I need to say something about a squared difference, I'm going to say, well, we're going to handle that by analyzing A minus C squared and C minus B squared. And that's where that's coming from. Okay. So we're going to bound this quantity cell by cell. We have, so we are only going to have to focus on one cell, and the same analysis works for all of the cells. And in each cell, we're doing this by bounding terms of this form. I'm going to introduce some other quantity called lambda kx, and I'm using my fact now to split this up into p tilde minus lambda kx squared and p star minus lambda kx squared. So what is this lambda kx? Here it is formally. So the way to parse this is, remember that we're assuming that P star has the form W composed with H. So what we're asking about here is, what is the average true P star value for the members in, I'm analyzing a particular cell, S sub k. So for the members of SK, which are further contained in the level set of p tilde with value p tilde of x. So I'm taking inside of sk, I'm looking at the ones whose value is p tilde of x, and I'm asking about them. That's what lambda k x is. It's their expectation. Now, so again, we're looking at this and we're splitting it into an analysis of these guys and these guys. So the first kind is very simple. This is just going to be small by the multi-calibration condition, because p tilde of x is multi-calibrated with respect to the cells. In particular, it says that within cell sk, if we look at all of the people who were assigned by p tilde the value v, then their average truth is v. So that's exactly what that says. So I don't have to worry about these guys. So now we're going to need to look at these guys. And these are much weirder, because this is p star, not p tilde. And yeah, so we're going to have to break this down further. I have a little graphic. It might help you. It might not help you. So here's my cell, sk. And we were looking at the level sets of p tilde within that cell. And we are, this quantity, lambda k of x, is just the average p star for the level sets of p tilde within cell k. This picture will change in a moment. All right. So we have to look at these guys. And again, we're going to use this trick of splitting this into two different kinds of terms. First of all, here, I've taken p star of x, and I've replaced it with its pieces, because p star is w composed with h. And this is still our old lambda k. And I'm expressing this now in terms of what? Sorry. Great. Okay, what have I thrown in here that's different? I've thrown in this thing, which has a hat on it, here and here. So here's my left term, and then over here is my right term, and now I've thrown in this guy with the hats on the h instead of no hat on the h. Well, this piece we can understand very well because by assumption we have some guarantee about the goodness of h hat. And the guarantee about the goodness of h hat controls this difference in terms of the Lipschitz constraints on h. So I don't have to worry about those terms. Those are handled by goodness of h hat. So now I'm going to define a different quantity. Instead of lambda k over here, I'm going to say, well, I'm going to define a new quantity, and I'm going to take this term on the right, and I'm going to again split it into two pieces. I'm going to throw in this lambda k here, lambda prime k here, and lambda prime k here. So what is this thing? Here's the formal definition. It looks a lot like the definition of lambda k, only I have h hat now instead of h. And so lambda prime sub k on x is the average truth, the average p star value, on the level sets of p tilde, but not really in the real world, not the real p star, but in a world where the truth is actually given not by w composed with h, but instead by w composed with h prime. So if we changed reality a little bit, what would we have here? And we handle this term through a bound on the diameter of the cells, which we built, together with the technical condition, which helps us make sure that that diameter isn't too big. And actually, that's the end, because this piece, again, is handled by the EH goodness of H prime. So that's the shape of how the analysis goes. And what we can show, well, I guess I showed you the theorem earlier. And I just want to make a comment here. So a lot of times, people may make a learnability assumption. The form of a learnability assumption would be essentially that as n gets large enough, then the error EH, the goodness violation, will shrink, go to 0. And under the learnability assumption, our result gives this kind of an error, and that's actually a minimax bound. And notice that I've got this n to the minus 2 beta over stuff over here. N is n, it's the number of samples, L is a constant, R we're thinking of as a small constant like 5 or something like that. So, so we get something that's sort of asymptotically tight. Okay, so that's what that's the approach. And there are some well-studied cases in which learning H hat can be very, very easy, and a lot easier perhaps than learning P star. So I know this looks really crazy, but you might have a neural net that first computes some linear mapping and gets things down to one dimension, and then does various Lipschitz things to it. And while that sounds really nuts, I think this is what's done in the single index models, and I had another example which I forget at the moment. And when you do something like this, you can actually get your hands on H hat using ordinary least squares minimization. So very, very easy to get your hands on such an H hat. So when P star has a nice enough form, you can definitely do this. Let's see. And the error bounds that you get look like this when the x's are drawn, say, from symmetric sub-Gaussian distributions with bounded eigenvalues. That's often the case in image recognition. So this would be a case. Another situation that makes learning H hat easy, or can make learning H hat easy, is when we're looking at a transfer learning setting. So in transfer learning, the intuition is that you have a bunch of tasks that are related, and you learn some kind of a low-dimensional representation of your data, and then you apply different suffix networks according to which of the tasks you are interested in solving. So, and this kind of approach is taken both when in your different tasks you're maybe dealing with different distributions, but you have the same functional relationships between x and y. That's the covariate shift setting. Or it could be in the concept shift setting where the relationship between x and y does change from one domain to another. So the approach that we could use then, again, taken from the literature, is that for each source distribution, you might not have a lot of training data for each source distribution, but the whole point in transfer learning is to leverage the related examples from the related tasks and borrow strength and get to the point where you're acting as if you have a lot of data. So you can, for each task, we could build a linear model and then compute the SVD of our collection of models and take some top right, left top R was our number, B to the R was our number of sets, singular vectors. And then using results from the literature, you can get to this kind of an error. Again, this is low dimensional, this is your number of tasks, and n is large. Okay, and I want to skip this slide. Okay, so wrapping this part up, scaffolding sets, when they work out, will give you kind of pan-fairness for all subsets, astonishingly, or almost all large subsets via multi-calibration. If we did it in the normal way, it might be very expensive. If you have a solution to the scaffolding sets problem, then it's inexpensive. So before we said that complexity theory rocks in terms of being able to articulate, to name different subpopulations. Now we're saying accuracy rocks as a run around having to name all of these populations. Sometimes you can easily find this collection using a good low-dimensional representation, and we get power. So that's what I wanted to say about scaffolding sets. And if there are no questions on this, I'll go on to a completely different topic. What did we do? We started at 10:30?
Yeah, we were supposed to go till 11:45.
Should I? People look really exhausted. I have not seen you look so exhausted the entire previous until now. Unless there's a strong objection, I will proceed. Yeah, Chelsea. Wait.
A quick
sorry.
question. Has there been empirical studies and have you seen any correlation or any sort of meaning for the sets that were identified through this to sort of...
So you're saying, did we come up with meaningful other sets by playing with this? We have not done those experiments. And we're never going to be the point is not to have to list the demographically sensitive sets, so to speak. The point is just to try to come up with level sets. And we did do some toy examples where we were definitely getting somewhere, but using MNIST sort of stuff.
Okay, I was just curious if that sort of has any sort of a relationship with like historically disadvantaged groups, like if there is some sort of I know that is not the aim here, but post hoc, would it be meaningful to do that, maybe to establish trust with the users or something, like just to understand, like from a psychological point of view, doing an empirical analysis and then looking post hoc how what kinds of sets get identified as the ones with the most nudges, for instance. Would that be worthwhile, or do you think we should not get into that space at all?
I don't know the answer to your question, because I think you're asking me about something that's kind of not technical and is more an interaction with human question, right? And at best I could speculate, but I really don't feel that I know the answer.
Okay.
Yeah.
This is also not a math question, but you mentioned false consciousness earlier.
Yeah.
I know there are, I don't know much about it, but I know there are several different definitions in philosophy. Was there a working definition that you had?
No, there is not. What I kind of got to this path. Thanks for the question. I got to this path because I was in a lecture about a particular religious thinker and writer, and I don't remember what century she was from. And the person who was giving the talk quoted this woman, quoted her writings, where she starts by saying something to the effect of, I know I can't really have any meaningful thoughts about this because I'm a woman. And I thought, I wonder if she really believed it or if it was just tongue-in-cheek. So that's when I started kind of questioning whether even if members of a subordinated group had lots and lots of energy, would they necessarily be able to note that they were in this situation? And then I talked to Mahzreen Banerjee, who was one of the authors of this Jost and Banerjee paper, about whether this kind of thing really happens, and she sent me to this paper. That's more or less the extent of my knowledge and how I got there. Yeah. Okay. So, great. So in the last couple of minutes, I'm going to talk on a completely different area, which is called fair representation. So fair representation learning. It's a group-based notion, and you know our various skepticisms about that. I still think it's really interesting, and I think it has a lot of great applications to geographically scattered groups, and you can ask me about that separately. But the idea is, so geographically separated, not sensitive in any way, just, yes, far-flung. Okay? So the idea was, is it possible to learn what we called a fair representation of the data, which again would be some kind of transformation. You have humans, they get represented to the algorithms, and now we want to change, let's call that space X, the way things look to the algorithms. We want to find a mapping from X to some other space Z, and this mapping is going to do a couple of things. One is it's going to stamp out the sensitive information, which you could think of as censoring the sensitive information, and yet it should retain sufficient information about the individual to permit standard training for a variety of tasks. So that was the general idea. And we proposed some particular technique for doing this, and we did try in our work to ensure that similar people would be mapped similarly. But that aspect, similar mapped similarly, that is gone from the literature now. If you look at all of the papers that are being written about this sort of thing now, they've all lost track of the similarly aspect, which makes me cry. But, so Edwards and Storkey took this idea and said, yeah, let's frame the goal in terms of adversarial learning. So, and we're going to throw GANs at it. So does everybody know, is there someone who doesn't know the definition of a generative adversarial network? Great, okay. So if I tell you the abstract version, you'll miss all the fun. So here's the way I think about it that always lets me remember what's going on. Think about Pixar or some kind of movie, a company that is producing movies, and it's all kind of digital. So they want to have an image of a field, and the field has grass in it, and they need to find some way of generating images of blades of grass that look natural, because they don't have those images. So what they do is you imagine that you have these two dueling neural nets, and one of them is generating images, and the other one is being fed sometimes images that are being generated and sometimes images that were taken from some library of images of blades of grass, and it tries to distinguish. So given an image, is it generated or was it from the library? Is it real or is it bogus? If the adversary is successful, then the generating algorithm is told, you're failing, you need to do better. And it makes adjustments and tries again. And so the adversary's success at distinguishing provides some helpful feedback to the generator of the images. And the generator's ability to fool the adversary, I don't know why I said that last bullet, just ignore it. So remember that the adversary is being implemented in a neural net. So all we know at the end is that this neural net was not able to distinguish. Doesn't mean that you couldn't retrain some neural net of the same structure to do the distinguishing. It doesn't mean that if it may be that if you made the neural net just slightly more powerful, it would be able to do a much better job at distinguishing, but we know that it fools this one. So the idea then, as rephrased by Edwards and Storkey, is you have your data representation here, X. This is your space of representations of people to the algorithm. And here's a subset of the population. So humans mapped to S is a subset of the population. And you run this through an encoding algorithm. And the goal of the encoding algorithm is to hide membership in S. So that's the censoring step. On the other hand, you're also trying to train a predictor. So you want that you haven't stamped out so much information that prediction is impossible. So we pass through the encoder, it tries to hide the membership bit, but still permit prediction on Z. A decoder, indicated over here, will in fact try to, from Z, reconstruct as much of X as it can. It won't be able to reconstruct all of X because something was lost when we squeezed it down or when we did the censoring step. But remember that one of the goals is that you want to retain enough information to maybe even carry out other tasks later. So you want to reconstruct as much as you can. We have the adversary who tries to distinguish encodings of members of S from encodings of members of S complement. So those are the three important pieces. The predictor tries to predict given the representation, the decoder tries to reconstruct, and the adversary tries to distinguish. Yes?
I'm still trying to figure out how the adversarial and the decoder are doing separate jobs.
How the what?
How the adversarial and decoder are doing separate jobs. It looks like they're basically doing the same thing. Are they not?
So the decoder is, the adversary is only looking for one bit. Is this person in S or S complement?
Right.
The decoder is trying to reconstruct as much of this person's information as possible. Ideally, it would be without revealing the membership bit in S. But let's say maybe it has a bunch of credit information and information that could be used for other financial tasks. So when you do the training, you want to have a loss, a penalty for inability to reconstruct, to decode. But you also have a penalty for being able to distinguish S from S complement. So you're trying to solve all three, and you have a penalty for failing to predict. So you're trying to solve all of these things at once and balance them against each other. Is that helping?
I was just thinking the adversary could use the decoder to do the distinguishing job. Is that?
But let's suppose that the outcome of all of this was to retain lots of information that is useful for determining creditworthiness, but at the same time not reconstruct sex. So they're not really trying to do the same thing. The decoder wants to, helping, not helping? And anybody else is welcome to try to help me explain. Yeah.
Maybe one way to think of it is coupled and decoupled weights. You want to give one of them weights to learn another task and then have independent weights to learn the second task about predicting the gender. And maybe you could do it with one, but you're reducing the degrees of freedom. So that might be a harder task overall.
I see. So they could, in a way, be doing similar jobs, but also you can have different objective for the two parties.
Right.
Okay.
Right. Good. Thank you so much. Okay. So there's a fair amount of literature on things that look like this. And the usual framework is, well, here's how we do this, here's how we train. These are the loss functions we're using. We're using hinge loss. We're using this kind of a network. We're using cross entropy, whatever. And they'll be filled with things like, this structure encourages, this penalty encourages the censoring of the sensitive bit. This part encourages the ability to reconstruct. But, it's very hard to really sink your teeth into things. So in this paper by Madras et al., Learning Adversarially Fair and Transferable Representations, they actually prove some pretty interesting statements. So I want to tell you a little bit about their architecture, and then at least give you the flavor of one of their theorems. This was a 2018 paper. Okay, so can you see the picture? Pretty well? Good. So let's just go through it. It's got more or less the same pieces that we saw before, but this is the architecture that their paper is dealing with. So here's your space X of like the real data representation that you start with. And then X gets passed through an encoder, and the resulting space is here, is Z. It might be, say, I find it helpful to think of it as lower dimensional. It doesn't have to be lower dimensional, but it's a helpful thought. And if you have some distribution on X, you get, of course, an induced distribution here on Z. Now, when you have this new representation of the individual, you could pass this to the classifier, who tries to predict whether the outcome will be 0 or 1 for this person. The prediction is called Y. You can also take this representation and pass it to the adversary, and the adversary is going to try to guess the sensitive attribute A. Is it 0 or 1? And then feedback can happen. Let me see, encoder maps X. Right. Then also, when we've taken this we've done this encoding to Z, we can also give that back to the decoder, who tries to get X back again here. And the decoder could optionally get the guess about the sensitive attribute. They look at these are the pieces of the model, and then you look at various combinations of them. So this is kind of an optional inclusion here. And this is what the network looks like. Okay? Any questions? All right. So here's their optimization problem. They want to minimize over all encodings, classifiers, G, and decodings. The worst case adversarial, the worst case over all adversaries, the following loss term. So what does this loss term have? The loss function have. It has 3 terms. The first term, L sub C, is classification loss. So they want to minimize the classification loss. The next term is the decoding loss. They want the decoded thing, which is K of f of xa comma a. They want that to look as close to x as possible. And then they have a sorry, let me make sure I've got this right. What is R? R should, the reward that's given to the adversary. R stands for reward. These guys are losses, these guys are rewards. So you want to minimize the adversary's reward. The adversary is going to win when it correctly guesses the sensitive attribute, and it loses when it incorrectly guesses the sensitive attribute. And so you want to reduce its reward. So that's what they're studying. And different choices for the fairness loss function R will capture different group fairness notions. So they're now going to formally tie the form of this function to specific things like statistical parity, false positive rate equivalence, maybe false negative rate, and so on. And we'll look at the statistical parity version. Yes?
Why do we need actually the decoder, the decoding step?
What they want, good. So the question is, why do they have the decoding step? One of the look at the name of the paper again. Learning adversarially fair and transferable representations. So they want to say, we've taken the distribution, we've wrung out some things that we don't think should be entering certain kinds of decisions, and we're giving you a new representation that's still very rich and that lets you do a lot. Yes, we're going to use it for this particular first task, G, but you might want to use it for some other related tasks in the future. Like in the previous part of the talk, I talked about how when you, in transfer learning, you have these different distributions and you want a mapping that's common among them. That's what it's for. Great, yes?
There is a redundancy there, because if you can reconstruct X again, then you don't really need to use the loss there over the classifier, right? Because you could potentially run a classifier over the X hat, the reconstruction. So yes, there is...
Good.
Another,
Sure, speak up.
relates to what we talked yesterday. So,
Yeah.
A different objective would be, instead of not trying to reconstruct X, but trying to have a very compressed representation Z. So it wouldn't allow you to reconstruct X, but it will keep the necessary information to run the classifier, but still not having the information.
So here I have to interject something, which is, and this freaks me out and I don't know how to think about it. Suppose when you learn the representation, all you do is you learn to predict. And so the representation of positive instances is 1, and the representation of negative instances is 0, and we don't need the predictor, and it's like, so one of the things that, there are situations where if you're going to try using this for transfer learning, you don't want that because the behavior, the mapping from X to Y may be quite different in your new distribution. So by having the reconstruction term there, you force it not to get rid of all of the information and reduce down to a single bit. Make sense?
Yeah, what I'm saying is that if you are using that loss over the classifier, or otherwise, the other one, if you want a good reconstruction of X, you don't have to add that term, that loss of the classifier, or you could look at a different task, that is, I want to have a concise representation of X. And yes, of course, you can go to the extremes. The representation, the relevant representation of X would be just the answer of the classifier.
Right.
That is.
Yeah, but my point is, if you do that, then you don't have this thing available for transfer learning. You don't have anything useful available for transfer learning. And this is the point of the decoder. Okay. All right.
Can I ask a follow-up?
Sure.
So where does the representation for transferring come from? Is it the output of the decoder or the input of the decoder? Yeah.
What was the question? Sorry.
Oh, yes. So what is the representation that is used for transfer learning? Is it the output of the decoder or the input?
The output of the decoder. I'm sorry. Sorry. No. The output of the encoder. It's this mapping down.
Okay.
Do I believe this? Hold on. No, I don't believe what I just said. What do you say? It's
Absolutely.
It's the decoder.
Imagine what you have there. If you have
Right.
Z,
Right.
you have all
It's
the necessary
Z.
information, and you don't want to go back to reconstructing X, and then again
Right.
having some other representation.
Yes.
So you have the information there.
Right. Yeah. But forcing you to be able to blow it up back to X is what makes sure it stays informative. Otherwise, you could get it down to something that was too trivial.
Right.
Yeah.
Also,
Let's see. Oops.
if say we had a distance metric for individual fairness,
Uh-huh.
is there hope that we might be able to use this model in some ways? There's something fundamentally group that is baked into this.
Great. Is there something that's fundamentally group E that's baked into this, or is there any way that we could use?
Like
If we had our hands on the metric, you could probably, I'm guessing here, maybe somebody else knows better, you could probably add to the penalty a penalty for mapping similar people to very different representations, something like that, but I'm not sure.
Okay, so you'd be penalizing.
Mm-hmm.
Okay.
Penalizing violations, yeah. There was a question here? No? How about you?
Yeah, could you use this representation that has, stamped out those specific characteristics that you didn't want to have to construct a metric?
Could you use the representation that is now censored to construct a metric? I think it's a good question, and I don't know. I think it's a very good question. Yeah. Yes?
Why are you feeding the decoder with the information provided by the adversary if your final aim is to fool the adversary?
I don't think I understood the question. Could you try again?
Yeah. You are taking the outcome of the adversary and also using in the decoder?
I'm taking the adversary, yes. You could use it in the decoder, yes.
Yeah, so why do you use that information if your final objective is to fool the adversary, like not to trust on the adversary?
So, do you want to answer this?
Yes, it's because you want to reconstruct X, and you won't be able to do that if you took out the information, the sensitive information. So you're just helping the decoder so you can have the loss on Z so that you could potentially reconstruct it. If somebody gives you the side information about the sensitive property. That's it.
Any other questions? Yeah.
In a way, you don't necessarily need the adversary if it's just like neural networks, right? You can just like concatenate those neural networks together.
I'm sorry, you don't need the adversary
For the decoder.
for the decoder. Good. So my understanding is that it's optional. The adversary's input to the decoder is optional. And as I mentioned, there are these different parts, and you can, in a different setting, we've experimented with lots of different subsets of these parts to see which ones were working for what we wanted to do. And I think that the paper also is pretty clear that they're not trying to say you must do things exactly this way. They're saying here's an architecture that you can play with. That's my understanding. Okay. Great. So, so here is a loss function for demographic parity. Remember that H is the adversary. The adversary takes the representation and is trying to guess the value of A. So the loss function for H is given by this expression. So DI, we have D0 and D1. Say D0 are from the distribution on people in S, and D1 is the distribution on people in S complement. So we're looking at the sum of the expected losses on each of these two. Yes, great. Note that if the population is 50-50 and censoring is perfect, the adversary's loss is going to be 0. Okay. If things are very biased, just as Guy was discussing earlier today, the adversary can do well. Okay, so we actually just have a couple of equations. So I think we'll be done in less than 5 minutes. Suppose we have some kind of a neural net or a circuit or whatever you want called mu. So we're going to define the difference, the distinguishing ability of mu to be, so mu is going to map things in some distribution to 0 or 1. And this is capturing the ability to distinguish, the difference in the probability of outputting a 1 when we draw from D0 versus outputting 1 when we draw from D1, absolute value of those differences. And then you're used to the statistical distance, so they take a very kind of machine learning view of this and say the statistical distance is defined as the maximum attainable test discrepancy, where they've defined this to be the test discrepancy. Mu is the test. So this is kind of the best distinguishing that's possible ever. It's the supremum over all possible tests of this difference. Okay. That's so, as we said, this distribution on X, when we pass it through the encoder, is inducing a distribution on Z. So we're going to let Z naught be what happens when we pass through instances that are not in the set S, and Z1 will be the distribution when we have, sorry. Yes, this is exactly right, yeah. And this is going to be the distribution when we pass through people who are in the other set, the complement, okay? So D0, D1 give rise naturally to Z0, Z1 respectively. And now we're interested in the extent to which the classifier G itself is a distinguisher. Right? If your classifier somehow is unfair, then you might feel that part of what it's doing is actually distinguishing who's in S and who's in T. So in any case, either way, it's a distinguisher. Its ability to distinguish is a measure of the way in which the classifications are not satisfying statistical parity. And as the authors point out, you're going to get a 0 here if and only if demographic parity has been achieved. Same probability of 1 whether you're in Z0 or in Z1. So now let's consider a particular adversary H, which is just has this objective function. So what is this objective function? This adversary's reward is on, notice that on Z0, this adversary will win when H is 0. And on Z1, it will win if it outputs a 1. And this again was our definition of the statistical, the departure from demographic parity of the classifier G. So suppose that is greater than 0, and without loss of generality, let's assume that this is the bigger term, so we can forget about the absolute values. So then we get that this difference is expressed here. And now let's take H to be 1 minus G. So we're going to choose H to be 1 minus G, and then this becomes the reward or the advantage of H. And now just notice that the optimal adversary H star will do at least as well as an arbitrary choice of H. And so we'll have that the adversary's reward will be at least the distinguishing capability here. So what they're saying is that, this will give us the following theorem. If we use these loss functions, if we use the loss function that they are proposing, and you train, then you will drive the true demographic parity violation to 0 if you train enough and have enough data. So they prove similar things. They show how to choose different loss functions if you want to achieve different notions of group fairness. And that's it. Okay.